Hello everyone, and welcome to your AP Physics 1 prep session number 1 of 3, I should add. We have, of course, our hour or so together today, and then we also have 2 subsequent sessions coming up in the next couple of weeks. Those would be on April 13th and 22nd, both at 6 p.m. Eastern Time. So if you're interested in checking those out as well as today's session, please feel free to show up then. What we want to get into for today's session, though, is a little look at the test in general first. So we'll look at the test overview, we'll look at its structure, some of those ideas when it comes to the test, and then we'll talk about some general test strategies, things we can make use of to help boost our score without necessarily mastering more content. So it's always great to have those strategies at hand. And then after that, we'll start to get into the actual content itself. And so for today's session, that means touching on ideas from kinematics. So the other bits of content that you'll be tested on, we'll cover those pieces of content in those subsequent sessions on April 13th and April 22nd. So my name is Dave, right? That's me, right? Same as the guy in the camera. But I've been a veteran course instructor, tutor and content developer with the Princeton Review in some capacity or other since 2004. So a very long time with this group and a very long time helping students achieve their desired test scores. My background itself is physics. So when you pair the experience with these tests with the experience and the content, in theory, you should be in good hands, right? Which says if you have any questions, don't hesitate to ask. Right, either Shadna in your who's monitoring the chat box or myself here should be able to supply with an answer, or at the very least direct you to where you can get some more information. In terms of my experience with these AP styles of tests, I should point out that I've been working with AP Physics 1, 2, and C, as well as Calculus AB and BC for a number of years now. So I'm quite familiar with the AP tests. And then for other tests, I also tutor and teach courses and develop content for other test types, including MCAT, DAT, OAT, GMAT, SAT, and ACT. So basically, if you took any 3 or 4 letters from the alphabet, smashed them together, you'd probably create a test name that I probably help people with. So again, needless to say, if you have questions, just go ahead and ask. More than happy to try to help out in that regard. And I should also point out before I forget, the resources you have available to you are actually plenty, right? For instance, if you want a review of the content you need to know for the test, as well as a bank of practice questions and practice tests, I would draw your attention to the AP Physics 1 Princeton Review Prep Book, which you can find at bookstores and online retailers, right? It's a great resource. I'm not biased by any means. But then also you've got the College Board AP Physics website. Right there, you get all kinds of amazing information, including the content you need to know for the test, the structures of the tests, when the test is being offered, which is important to know if you want to write it, as well as past tests. And you don't only just have access to past tests, you get those tests with solutions. And you don't just get the solutions, you get the grading rubric for the solutions, which tells you exactly what you need to do to earn those points and what's required of you to get them, and maybe what you don't want to do, so that way you don't lose those points. So very valuable resource at College Board website. Shadna, you present me this first question, right? I see it. Do I have to know electric dipole and AP Physics C, electricity and magnetism, such as dipole and electric field and potential due to electric dipole? Well, what we're covering today is a review of AP Physics 1, right? So let's just stick to that conversation here. But if you're taking AP Physics C, electricity and magnetism, then what's on College Board's website for what to know for the test this year for AP Physics C is what you want to stick to, right? All right, so let's get into our review. And speaking of content, let's take a look at a list of content for AP Physics 1. So the course content itself, in terms of material that gets covered in class, we have 10 units that are listed here, including kinematics, so likely things like uniformly accelerated motion, dynamics, which brings up Newton's laws, circular motion and gravitation, energy, which would bring in ideas of work, power, and conservation of energy, momentum, So think about things like conservation of momentum, collisions, impulse, simple harmonic motion, so springs and pendulums, torque and rotational motion, electric charge and electric force, like Coulomb's law, DC circuits, which would bring in ideas like Ohm's law and Kirchhoff's laws, and then mechanical waves and sound. So you look at that list, and that's a lot of material, right? It's a lot of things to have to know for the test. Well, perhaps thankfully, and you can see this on College Board's website as well for AP Physics 1. Units 8 through 10 are no longer tested on AP Physics 1. So you can cover them in class, but they won't be tested on the actual test itself. So instead, the material you're held responsible for knowing for the test are units 1 through 7. So do keep that in mind when it comes time to study for the test. In terms of how much of each of those different topics you'll see on the test, you can also find information on College Board's AP Physics 1 website, um, information on the exam weighting for the multiple choice section. So here we have this range of percentages giving you a sense of how heavily each item would be tested. Now, for some of you out there, I don't know if you're doing this or not, but if you're adding up the percentages, right, looking at these upper bounds, if you add up those upper bounds, they actually add to 100%, which may make you question how do these percentages work. But the percentages here are taken from the list that also included percentages from units 8, 9, and 10, which at one point the thought was to test those, right? So what the College Board says is uh, the proportional relationship found here is something that will still be consistent in terms of the representation for the topics. So try not to look at the numbers as a precise range. Just look at it more as a proportional representation. So for instance, you can get a sense that topics in energy and dynamics are going to be most heavily tested, whereas topics in kinematics, momentum, and torque and rotational motion will still have good representation on the test, but not quite as heavily tested as, say, dynamics and energy. And then circular motion and gravitation, along with simple harmonic motion, will have lesser representation, so fewer questions in the multiple choice section on those topics. So that's important to note because you want to think about yourself as an individual test taker, right? What are your known strengths? What are your known weaknesses? How much are the different topics likely to be tested based on this weighting, so that way you can get a sense strategically going forward when you study, how should you best distribute that study time amongst the various topics, right? And now let's talk about the test itself. So there's a sense of what will be on the test in terms of content, but let's see how the test is formatted. um, Another question, does APC, so like AP Physics C, go over concepts that are in AP Physics 1 and 2 except with calculus instead of algebra? Largely yes. Um, so for an exact collection of differences between the tests, again, you can check out College Board's website to get that contrast. But largely, yes, there's a real overlap in terms of the material that's covered. But AP Physics C goes certainly into more detail in terms of the math. Like they hold you responsible for calculus as opposed to AP Physics 1, which is more centered on algebra. So one way that you can take the test is as a paper and pencil test, which you would do in school. And that test is broken down into a couple of sections. The first section is a multiple choice section. So you'll have 50 questions to tackle in an hour and a half. So in terms of pacing, if we're curious about, how much time do I have per question? Well, you do the math, you put this together, and you'll find that you have 1 minute and 48 seconds per question. So that's the pacing you'd have, which is important to know because in terms of prepping for the test, you might want to work not just on the content, but also that pacing and time management. So if you needed a bank of practice multiple choice questions to look at, you could turn to the Princeton Reviews AP Physics 1 prep book, right? A lot of good examples there. Um, so this multiple choice section makes up 50% of the exam score. I would anticipate the first 45 of these multiple choice questions are your typical multiple choice problems, right? So 4 answer choices, A through D, and just 1 answer choice is correct. 5, and I anticipate those final 5 multiple choice questions would actually be multi-select questions where there are actually 2 correct options, and you need to find both of those to get the credit for the question. And some of your multiple choice questions will come as a set. which is to say they'll share some sort of information. So it could be that you're presented with maybe like a velocity versus time graph. And in the description of the graph, I might say, questions 7 to 9 relate to this velocity versus time graph. And it's important to note that because if you get to question 9 and it asks you to find a displacement and you say to yourself, well, gosh, how do I find that? I don't have enough information. Where's the information coming from? You might have to just leave it blank and move on, right? But if you could keep note of the fact that, hey, question 9 related back to that velocity versus time graph, then you get the displacement from the area under the curve. So do make a note when you get that shared bit of information, whether it is a graph, like I said, or maybe a table of values or some sort of word problem or something. Be very clear on what questions relate to it, right? So that's our first section. Our second section is a free response section. So here you'll have 5 questions to answer in an hour and a half. This is again worth 50% of the exam score. So each section is worth half of your total score. But here by free response, what we mean is now you actually have to show your work. So you might have to like do a bit of math or some algebra, right? Deriving a certain result, and you actually have to show the steps you went through to get that expression. You might have to write a short paragraph, sort of conceptual analysis, just talking about the ideas that are relevant, as opposed to maybe working through the technical, math exercises. But there's still work to be shown. Um, so the kinds of questions you get in free response include things like qualitative and quantitative analysis, like I said, where you could have to, work through some math, crunch a number, show that work, or just talk conceptually about the physics in a short paragraph answer. I would also anticipate you have a question that is an experimental design question, which is one that would ask you to design an experiment, like the name says. So you might have it so that a student has, like in the question, a student has a certain hypothesis, and your goal as a test taker is to say, what materials would I need to come up with an experiment to test the hypothesis, right? What are the steps of the procedure? How would I verify the hypothesis or disprove it, right? Maybe maybe they would provide you with some data from a sample experiment, and then you have to plot the data and then maybe interpret it somehow, something like that. But if you want more clarity on what these kinds of questions look like, well, you do have a few resources. For instance, we have a collection of free response questions available in our AP Physics 1 prep book from the Princeton Review. Um, but also the College Board's website. Like I said, they publish their past exams. So you can take a look at the different questions that have been asked before to see how they ask their questions, what styles of questions there are, and where to earn those points, right? Because they give those grading rubrics. So these paper and pencil in-school tests are offered at the following dates. The first is Wednesday, May 5th at 12 p.m. local time. Then there's also a Monday, May 24th date, 12 p.m. local time. The other format that's available to us is a digital online test, which can be taken either in person or at home. And this has a slightly different structure. So not for the first section, though. This is still multiple choice, and everything looks the same as it is for the paper and pencil test. So 50 questions to tackle in an hour and a half. So again, that gives us a minute and 48 seconds per question. The first section is worth 50% of the exam score. 45 of your questions will be single correct answer questions. The other 5 will be multi-select questions where 2 of the options are actually correct. Some of the questions will come as a paired set where they have some sort of information that they share in common. And it's important to note that so that way, again, you keep track of the fact that the information relates to a couple of questions. But the second section is where we get some differences. So in our second section, we again have those free response questions, but now we also get some multiple choice problems. So the first portion here will be a selection of 25 multiple choice questions in which we have 45 minutes to answer them. So for the pacing this time around, you work out the math and it's identical to what we had before. 1 minute, 48 seconds per question. For the free response questions, instead of 5, you have 2 and 45 minutes to tackle those. So Those two free response questions, again, I'd anticipate something like qualitative and quantitative analysis, where, again, you might have to show some work going through some math, be that algebra or computation or both, but also having to discuss ideas in a short answer, more conceptual kind of framework. And I would anticipate one of those two questions to be that experimental design question. So do bear that in mind. And this is an hour and a half. So in total, this test, in either version, is a 3-hour test. So it's a long test, maybe longer than some of the exams we might have experienced before. And that's important to note, because it's one thing to say, well, I know the content and I can do a one-off Newton's laws problem, or a handful of multiple choice questions. It's another thing to have to, sorry, switch gears mentally between energy and momentum and Newton's laws and rotation, and do so over these different formats with multiple choice and free response in over a 3-hour window. So one thing that's very useful to getting used to doing that and to fighting fatigue over that 3-hour window is to simulate the test experience itself. And if we take a look at the Princeton Review's AP Physics 1 prep book, you'll see that it has a few different practice tests in there. It's the gray shading. I don't know why we see that, but there are a few practice tests there that you can take to simulate that test experience, um, to be able to fight fatigue and know what it's like to do those different questions all in one shot. Again, this is 50% of your exam score. And again, for the free response questions, you're going to need to show your work, right? So you should anticipate that. Now, in the past, meaning last year, this digital test was first made available, and that was in light of COVID-19, of course. And the way students could approach the test last year was they would actually be able to work everything out for themselves on paper and pencil at home at their desk. But then they would take a picture of the work and submit that, and that would be graded. That's not the case this year. You won't be doing that. Instead, the work you submit will be online. And so if you're putting together a short answer paragraph, um, kind of an answer to a question, you'd be typing that in. If you need to show work with math and you need specific mathematical symbols, they're available on screen for you to choose and put into your work. So that's taken care of for you. So everything would be done on the computer, right? So do keep that in mind. Um, and this test is made available Wednesday, June 9th, 4 p.m. local time. So that's a little look at the general test structure. Now what I want to do is say a few things about some general strategies that can help for multiple choice and free response questions. Before flipping that to that, though, I should again remind everyone, if you have questions, just ask. I'm more than happy to try to take those up. But let's talk about those multiple choice questions. So for the multiple choice questions, nothing says you have to do them in order, right? In fact, strategically, you shouldn't, right? So for instance, if in working the multiple choice questions, you get to question 2, and it's a question that's a little bit confusingly worded for you as a test taker. Maybe it's dealing with a topic that you're less familiar with, is more of a weaker area for you. Um, and the math isn't necessarily coming together. Don't stubbornly stay with the problem, right? Because when you do that, you're going to sink a lot of time into the question and not necessarily get the point back for all that effort. But you will run down the clock, which means now you have to go all the faster and start rushing. And that's going to be problematic on a few levels. So one, when we rush, it's easy to make silly mistakes, right? Sign mistakes, 2 times 3 is 5, that kind of thing. And that's going to make us leave points on the table that we otherwise would have had. Also, if we sink too much time into those questions that aren't working out that well for us, it might be that we don't have the time to actually get to the last so many questions, and now we won't be able to actually work them. And maybe for us, those last few questions could be an absolute dream question, which is basically a free point for us, right? Potentially. But now we're not getting that because of how we're stubbornly doing 1 and then 2 and then question 3 and so forth. So the advice is to answer the easy questions, easy questions. And I do want to be clear, this should be in quotes, because it's not as if there is an actual order of difficulty. So it's not like question 1 is easy and question, say, 40 is hard or anything like that. Each question is just a self-similar kind of question that they just deal with different topics. So when we say easy, it's really more easy for you as an individual test taker, right? So if it seems straightforward for you, place your strengths in terms of the content, we'll get that done, right? And anything that doesn't fit that, you skip. Save it for a second pass through. So now you'll be able to get to those questions, which should be points for you to get. And then on the second pass through, you can see what you can do with those later questions. So reorder the questions. But when you do that, be careful. If you're skipping questions, you need to skip bubbles on the Scantron sheet. It's nothing worse than saying, well, question 2 didn't go so well. I'm going to skip that, move on to question 3. You answer 3 and it was easy and you know you got it right, but then you submit the answer to 3 into 2's bubble, right? Don't do that. So be very careful. Like I said, if you're skipping questions, you have to skip bubbles too. So one way that we can make sure that we are skipping bubbles is to like shade in the bubbles, not one question at a time, but in blocks. So for instance, if the first page of questions has questions 1 through 4, we'll attempt all 4 and then bubble them in as a group. Because then you're more likely to say, okay, here's 1, that's A, 2 I skipped, okay, I'll skip that, 3 was C, and then 4 is D. So you're more likely to actually know to jump that bubble in the question you skipped. So it's safe, right? But then it's also actually good for time management. So if we're answering a question, taking the time to shade the bubble, answer the next question, take the time to shade the bubble, and so forth, as opposed to more quickly shading a bunch.
Dave, he is correct. There is no going back. You
Okay.
can't go back.
Okay.
The recommendation from AP is paper. Put your answers on paper and then go and then answer them at the very end if there's any that you're concerned about, but you cannot go back.
Okay. All right, welcome back, everyone. Sorry for the little technical issues there, but we're back now to talk about strategies with multiple choice section. So let's get back to that. And one thing we can notice about multiple choice sections, or any test that is multiple choice, is that process of elimination is a great way to approach the test. And this works on a few levels. So try not to be in the headspace of thinking that physics is just there's one way to do a problem and that's it. If you know it, you get the point. If you don't, well, then too bad, because it doesn't have to go that way. So process of elimination with multiple choice can help out here. So for instance, imagine you have more of a conceptual question and an answer choice asks you to consider the ramifications of the horizontal component of gravity. Well, there is no horizontal component of gravity, so you can just strike through that answer choice option. There's no way it's correct. And you could continue to work that question in that way. And so if you could eliminate 3 out of the 4 options, whatever that fourth option says, regardless of your understanding of what it says, it's going to have to be correct if you know the other 3 are wrong, right? And with multiple choice questions, that's how it goes, right? There's the right answer is right there for you, but it's surrounded by all of those wrong answers. And because there are more of them, they might be easier to find than the right answer. So go ahead and find them, right? Um, so that's one way in which process of elimination is useful. Another way in which it's useful, you could consider, say, like a number crunching question, right? So if thinking about the problem ahead of time before diving into the work, if you can realize that, the answer to the question should be a number that's, so large. Well, then any answer choice that's too small, you can say, well, there's no way that's going to be right. And then you could strike through that. And that's useful, again, on a few levels, because for one thing, those wrong options are probably the result of a common math error you could imagine. So if you just dive into the work and you set up the math and you work through it, you exert all that effort and then you finally crunch a number and then you see that in, say, option A, well, you're just going to pick A and go on and probably never look back, right? But if you thought about the question very briefly at the start and you struck through A because you knew it was too small, well, when you do all that work and you find A, but then you see that it's struck through on your test booklet, you'll say, oh, I must have done something wrong. And then you can go back to the math and be able to fix that error. So that way you don't fall for that trap answer. So that's another way in which this process of elimination is very beneficial to you. But also, let's say you just can't answer the question, right? Math isn't coming together, or somehow you don't know what to start with to set up the problem. Well, by at least doing some process of elimination from the start, you can get rid of, an option or two, and that's going to reduce the number of options available to you. So now when you guess and you move on, you're more likely to get the question correct and get the credit for the problem. And that's the next thing we touch on for multiple choice, is that for this test, if you can't answer a question, guess. A wrong answer and a blank answer are both worth 0 credit. So there's no harm guessing. So never leave anything blank on the multiple choice section. So that takes us through what I wanted to say about the multiple choice questions. For the free response questions, there's a few things we can make a note of here to help out. And one of the things you could look for in the free response questions to figure out how to present an answer is how the question was asked. So some of the language of the question gives you a sense of what's required of you as a test taker. So for instance, the word justify means an argument will be supported by some evidence. So if you have to justify a certain claim, you might want to point to a certain physical principle, like such and such must be true according to like conservation of energy. There's not necessarily any like great work or math to show or go through, but you're bringing up some sort of evidence to support the claim. Calculate means that you're expected to show some work to get to the final answer. So you set up conservation of energy, do some rearranging, maybe plug in some numbers, and calculate something, but you need to show the process from which you went from A to B. Derive similarly suggests that you have to start from some foundational principle or fundamental equation like Newton's second law or conservation of energy, and then proceed from there to derive a certain expression. What is in determine are indicators that work doesn't necessarily have to be shown to obtain full credit. Maybe you can show some work to help out, but maybe the idea here is more just let me state what must be correct, and you can kind of leave it at that, or maybe make a small claim about why you think you're correct. And it could be that the questions kind of break down in steps. And you'll see that if you look through past tests. They're pretty good at breaking up a problem into multiple parts. So the first part could be just saying, you make the assessment, which is correct. And then the next part could be where you have to justify it. And then after that, you might need to derive a precise equation to see if that matches up with what you thought was correct in theory, that kind of thing. We might also have to deal with graphical analysis. And if you're asked to sketch anything, that means you need to construct a graph, but it doesn't really require full precision. Instead, what a sketch needs are those key features that pick out the relationships embedded in the physics. So a sketch should have like a correct slope, for instance, maybe the intercepts as special points of interest, they should be included. Asymptotes should be dashed in. But we point out here numerical scaling or specific data points itself to plot. They're not required for a sketch. A plot, on the other hand, does require more precision. So if you're asked to plot something, then you need to actually input data points to the graph on a grid that's often provided for you, which oftentimes comes with a specific scale. But if it doesn't, then you can construct your own scale, make sure it's just appropriate for the data they give you, and always be clear on the units that give context to the numbers you're plotting. Right. So the sketch is more of a rough sketch. The plot is a little bit more precise. On your exam, any question that asks for a free body diagram or a force diagram wants you to include just the real physical forces. That's it, not the components, right? And as we point out here, and you'll see this if you go through the past test questions, questions are pretty good about saying so explicitly, like don't include the components. But whether they say so explicitly or not, don't include the components. If you're asked for a free body diagram, just give those actual real physical forces, because what the test is trying to assess is, do you know the forces that are present? Do you know where they're supposed to be acted? Do you have that kind of physics down correct? For a subsequent problem that might ask you to, set up Newton's second law and derive an expression. Well, for you as an individual, it might help to have a free body diagram with the components put into it. It would for me too. But don't mark up the free body diagram you submitted for the earlier part of the question. That needs to just be those real physical forces, and that's that. So if you want that like a free body diagram with the components, draw another set of free body diagrams to work with in that subsequent problem, and let that be a visual aid to help you work that problem from there. And as I said, some questions will require you to design an experiment and outline a procedure. And so here you have to provide an orderly sequence of statements that specifies the needed steps to investigate some sort of hypothesis, to come up with an answer to the question that's being posed. So like I said, oftentimes we'll have to, for the different parts of a question, think about the materials we might use that could be available in a typical high school physics lab. What the procedure might be as an experiment to try to test out a certain hypothesis you're presented with, what you'd have to do to test the hypothesis, that kind of thing. And like I said, these specific design and experiment question types you can see in the past exams. So go to College Board's AP Physics website, look through those past exams, and see what these questions look like and where they're rewarding points. And so what we can say in conclusion, for some advice and some strategies when it comes to the free response section, is to clearly explain and justify your answers. Meaning, if you need to justify your answers or show some work, be very clear on what it is you need to do to assess that result or to present it, and then do so in a very clear and concise manner, which kind of ties into this next point that says use only the space you need. So on the test, you'll be given a lot of space to work with, but that doesn't mean you have to use it, right? So make your point and then move on, right? Don't feel compelled to fill in that space. There's nothing worse than like quite clearly getting the physics right, but then being nervous about all the extra space. And so you just start writing stuff, right? Start filling in that space with other things that might be tangentially related. But then you start filling in that space with things that aren't correct or are too peripheral to the problem. And now it just looks like you don't understand what's going on. And now you don't get the point for the question. That's a shame, right? So like I said, make your point, be clear, and then you can move on to the next problem. Read the full question, right? I said that before with multiple choice. I'll say it again, but read the full question here for free response, because you want to know exactly what it is the question's after, right? Because it's easy when you're doing some math and you're doing some work for a problem to, work through a lot of material, right? And then you come to some neat little result and you think, oh, I must be done. And so you present that result, but it's only a partial result. There's that next step to the problem to actually answer the question they've asked. So keep the full question in mind, and also read the whole question to know exactly what you're responsible for doing. Like, do you have to show a lot of math and technical detail, or is it more of just point to the right concept and talk briefly about the concepts, right? So to figure out what the task actually is, read the full question. Use common sense, which is to say, think about your answer, right? Whether they ask you to assess your final result or not, you should assess it just to make sure you're doing it right. So for instance, if a question asks you to find the speed of an airplane and you find it's going faster than the speed of light, you've done something wrong. So go back through the math and check that out. If you're asked to find the mass of a baby and you find the mass is 1,000 kilograms, all right, you've done something wrong. So go back and check the work. So use that common sense to assess your results. Think like a grader, right? So when you're putting together your answers, think, for the question they've asked and the points that it's worth, where am I likely to be getting the points? What do I really need to show to get the full credit for the work? And again, the best way to know what your graders are looking for is to look at those past tests and the grading rubrics that the College Board publishes. So you can see where they were awarding points. Like if a question's worth 3 points, where did the 3 points come from? What do you need to show, right? And so with that experience with what they've demanded in the past, you can figure out what to do in the present on your current test. And think before you write. So again, you want to be able to make your point, be sure that it's correct. You're saying it in a clear and concise manner. So instead of just immediately putting pen to paper, where you might start scribbling a few things and maybe it's not quite the way you wanted to say it, so you have to erase it or scratch things out and start writing again. Instead of doing all that, just take a second, formulate the response in mind, and then work that out, in an appropriate way on the test paper itself. And also, not your answers don't just have to be clear and concise; they also have to be legible, right? Which is another reason why you want to think before you write. If you make a real mess trying to present your answer, it could be perfectly correct, very precise language, very concisely stated. But if it's an absolute mess and your grader can't read it, you're not going to get credit for it. So take the time to think about what you want to say, put it down appropriately, make your point, and then move on to that next problem. So that's a little look at some ideas for strategy for the free response section. And now what I think I'd like to switch to is the content. And like I said, what we're going to get into today for content is a little touch on kinematics. And when it comes to kinematics, what we should be very clear on are our definitions. Right, so in everyday settings, we often use these very technical terms from kinematics in very imprecise ways. And the test makers might try to exploit that imprecision in the use of language to have you fall for trap answers. So be very clear on the definitions. So as an example of that, we often use speed and velocity in everyday settings like they're identical, but they do have very separate meanings, and we have to be careful with that. So when it comes to definitions, let's start with distance versus displacement. So if we have an object traveling between 2 points, right, going from A to B, the distance is the length of the path actually traveled from point A to point B. So that would be the length of this winding blue curve. But the displacement is the length of the straight line path that connects where the object started to where the object finished. And it quotes direction. So displacement is a vector quantity. It's not just a numerical value, it has this direction associated with it, and it's independent of the actual path taken. So that red arrow could represent your displacement, which sometimes we call delta x vector, because your displacement really tells you what the change in your position was. And that's what delta x is reflecting. So notice these two terms, distance and displacement, again, things we might interchange in an everyday way of talking, are different. First off, displacement has direction, distance doesn't. And you can see numerically, these two things don't have to be the same. They could if two objects moved in a straight line, but they don't have to be. Like we see here, this winding blue curve is clearly a greater length than the length of that red arrow. So to help firmly establish that point, let's consider an example. Let's say we have a track and field event and an athlete runs exactly once around an ovular track with a total distance covered of 500 meters. So like we're showing above here, we've got our start position here. They're going to run around the track. And when they get back to where they started, that's their finish line. So based on this, we're asked to find the displacement for the race. Well, recall that the displacement tells you how different your final and initial positions are. So with that thinking in mind, can anyone tell me in the chat box, what is the displacement for our runner in this case? All right, we've got that 0. Yep, that's exactly it. Good. 0 meters, right? Because there is no change in the position. We start where we finish, therefore there is no displacement, right? There's no length between those points. So notice here again, these two quantities don't have to be numerically similar. And just because there's a great distance traveled, that doesn't mean that there needs to be a great displacement as well. So next up for definitions, we have average speed and average velocity. So an average speed is a measure of the distance covered per time taken. So here we've got a scalar quantity denoted by v, which is that distance per time. And so it would have units in SI of meters per second. An average velocity, on the other hand, is the displacement covered per time taken. So this means velocity is a vector quantity related to that displacement vector. So delta x per delta t, or d vector per t. And the units are meters per second. But if instead of looking at an average over a larger time frame, if we were curious about an instantaneous or moment-to-moment velocity, here's what we could claim, and I'll type this in for us. Instantaneous, uh, the instantaneous velocity is the object's speed with the direction at that moment. So that vector quantity there, remember, it's got those two pieces are vectors, right? It's got that magnitude, or that numerical amount. In the case of the instantaneous velocity, that'd be the speed. And then there's also the direction, which is where the object is moving in that moment. So let's think about that in terms of our runner going around the track. So let's assume our runner in that earlier example completes that one lap in 1 minute and 18 seconds. And what we need to do is find their average speed and average velocity. Well, looking at the time frame, we've got 1 minute and 18 seconds. So I got this mix of units now, minutes and seconds. For any computation question, for the multiple choice section, take a look at the answer choices to get some insights in terms of what units do I need, right? Is it meters per second, meters per minute, centimeters per second, right? It'll let you know if you need to convert, and if so, to what. So here, let's stick to SI units. So we've got 1 minute, which is 60 seconds, and then 18 more to get us 78 seconds. So for the speed we've been asked about, that would be distance per time. The distance the object traveled through was the 500 meters we noted in the previous example, and now the time frame for that is 78 seconds. So you'll have your calculator available. You can crunch this with a bit of precision, though it's worth noting you might be able to ballpark this based on answer choices that are available. But working this out, you'll find 6.41 meters per second. Now the velocity, remember, that's based on the displacement. So your velocity is that displacement per time. And of course, if there is no displacement, then on average, there is no velocity. So again, notice how these two quantities that we often interchange in an everyday way of speaking are very different, right? Again, for one, velocity has direction, speed doesn't, and these two quantities don't have to be numerically similar. So I have to be very careful with that. And then next up for our definitions, we have acceleration. And an average acceleration is the change in velocity experienced per time taken. So your acceleration vector is your delta v vector per delta t. And that delta, that change in any quantity, is always the final quantity minus the initial quantity. And then here for acceleration, we divide this by time. So in terms of these different quantities, we often say v subscript 0 for initial velocity, as in velocity at time 0, and sometimes we call that v naught. And then v without a subscript is a velocity at a later time. So that's your v final. And so the units would look like meters per second, or just meters per second squared. So let's consider this definition with our runner going around the track, right? We had that oval to run around. And let's make the following claim here. Let's say for one lap, what is the, and let's say this, for one lap at constant speed, what is the average acceleration? Ask that question first. And does anyone want to hazard a guess before we look through the details? What do we think? Going around this lap once at constant speed, what would the average acceleration be for that lap? Nothing yet? Well, let's talk about it a little bit. How about that? We'll walk through it. So recall here that your average acceleration looks like the change in velocity per time. So what the acceleration tells you is how different the velocity looks like over that time that you're averaging over, right? So for us, our object started at this start position, made its way around the track, and got to the final position back here. So the velocities for the initial and the final velocities are the velocity that we would have started with right here, and then the velocity we would have when we get back to that point. And let's be clear, those velocities in those instants would have the same magnitude because we're traveling at constant speed, right? In terms of the direction of the velocities, well, it's the velocity points where we're going. So for the runner, it's basically pointing where we're looking, or in general, the velocity is tangent to the path. So starting out, tangent to the path would point like this. But as time goes by and the runner's at a different position, tangent to the path could mean up like this, could mean to the left like this. But certainly when the runner comes back to the same position, tangent to the path would have to mean the same direction. So with that stated, what do we think the average acceleration would be for the track? Does anyone want to hazard a guess now? Right, it's going to be a 0, exactly, because the magnitudes of these two velocities are the same, and so are the directions, which means there is no difference or no change in the velocity. So on average, the acceleration would have to be 0. But how about the instantaneous acceleration? Like if we try to find the acceleration from moment to moment to moment, does anyone know, would that also be 0? No answers yet? So let me ask a separate question then. When we look moment to moment to moment to moment, is the direction of the velocity always the same? Ah, no, it's not, which means some part of our vector changes. Remember, your vector's got those two different pieces to it, right? It's got the magnitude and it's got the direction. And if any one of those pieces changes, your vector changes, right? So here there must be a change in the velocity because the direction changes, which means there must be an acceleration. So let's note that. The instantaneous or moment-to-moment acceleration, that is not 0. So part of the teaching point here is to realize that, yeah, we need to know the definitions to answer our questions. We've got to know the physics. But also it reminds us that this test is very much a reading test. So read the full question. Did it ask for displacement or distance? Speed or velocity? an average or an instantaneous quantity, right? Just that subtle little change in the odd word can really change the whole question and affect what answer choice is actually correct. So we need to read the full question to make sure we answer the actual question asked and get the point for the problem. All right, so are there any questions on what we covered there for our definitions in kinematics? Or any questions at all from tonight? Or this afternoon, I suppose? All right, because I think what we'll do is we'll cap the conversation here for tonight. So what I'll say is great job, everyone. There's some confetti to throw your way. Thanks for all the time you took out of your schedule to be here today, for the participation, for the few questions we asked. I greatly appreciate it. And remember, we have subsequent sessions to go over more content, right? We've got a session on April 13th and April 22nd at 6 p.m. Eastern time, where we'll go through the rest of the content. So make sure you show up for those sessions as well.